Okay, got it. Okay. So, okay, then maybe let me first introduce our speaker and then we start the presentation. Good morning, everyone. Welcome to our physics seminar. Today, we are very fortunate that we have a very young and promising professor from Beihang University, Professor Liu Zhiqi. Professor Liu Zhiqi graduated with his PhD from National University of Singapore in 2014. And then he conducted his postdoctoral research at Oak Ridge National Lab, Berkeley, as well as I think Los Alamos. Then after his productive postdoc researcher period, he moved to a very prestigious university, Beihang University in China. And currently he's a full professor in the university. Prof. Zhiqi, Liu Zhiqi's research field is very diverse, but it's majority covering the oxide interface as well as antiferromagnetic spintronics. In particular, in the field of antiferromagnetic spintronics, he is very well known. If you talk about the papers, he has already produced at least one Nature Nanotechnology, two Nature Electronics as corresponding or the first authors. But beyond that, there are so many other advanced materials, PRX, PRL, there are so many more. So to summarize Prof. Liu, if you have not heard his name before, you just need to try to remember his name, because he is a rising, promising star, and in future you will hear his name very often. Okay, so I think for now, that's about the introduction, and today his presentation is electrical field controlled antiferromagnetic spintronic devices. And great, so Zhiqi, now the stage is yours. Thank you very much, you can start.
Okay, great, thanks for the introduction. So it's really an honor to be here, and let me introduce our recent work as well as the related works performed by others. So today my topic is electric field controlled antiferromagnetic spintronic devices. I think this is a relatively new field. Most of studies were started like in 2016. After that, the number of studies becomes substantially increased in recent years. So I'm Zhiqi Liu from Beihang University at Beijing. The background for all the spintronic devices is indeed for information devices. That includes the data storage, the calculations similar to the CPU, and also now the in-memory computing, and also for sensors. So if we look at our data storage, most of data are stored in so-called data centers, which actually which are consistent by lots of hard disks. For the hard disks, we actually have very thin ferromagnetic thin films as the key storage media. For example, for our HDD, the key material for the hard disk is cobalt, chromium, platinum. That has a perpendicular magnetic anisotropy. So if your magnetization is up, that could represent 1, and if the magnetization of this bit over a small bit is done, that can represent 0. For the hard disk, the right head, its right head is a coil. It's just a simple cut coil. Its read head is a GMR sensor. But for writing the data in this hard disk, you have to inject a current into this coil. That means there will be significant Joule heating. Similarly, for our MRAM devices, that's actually could replace the DRAM for our current compute technology. For this MRAM device, the key elements are still ferromagnetic materials. For example, nickel, iron, cobalt. They are only few nanometers thick, maybe even like less than 10 nanometers thick. The feature area of this kind of MRAM devices is around 60 nanometer. But for writing the information in this kind of devices, you still need to inject the current, either using the spin transfer torque or using the spin opposite torque. Anyway, you have to use the current to generate a stimulus for the magnetization for current magnetic memory devices. That means the Joule heating is inevitable. As a result, the energy consumption for writing a bit for MRAM is still not. For example, for the conventional MRAM, you need a current to generate a magnetic field. That the energy consumption is 100 picojoule per bit. For the spin transfer torque MRAM, the energy consumption is significantly reduced by like around 100 times. It reaches you still need 1 picojoule for writing 1 bit. If we look at the electricity for data storage, as predicted by the International Data Corporation, in 2024, the electricity cost for the data storage could be more than 5% for the electricity of the entire society. That's actually a significant number. And then, under this background, we want to pursue an alternative approach. That means whether we can use electric field instead of the electrical current to control the magnetization for storing data. So what's the difference between the electrical field and an electrical current? If we apply an electric voltage to a conductor, that will literally generate an electrical current. So there's no difference then. But if we apply an electric voltage to an insulator, for example, a piezoelectric material or a ferroelectric oxide, the electric voltage could only generate the piezoelectric string rather than an electrical current. So we want to utilize a functional oxide, insulator oxide, so that the electric current is suppressed and then the Joule heating is suppressed. And then if we can combine the ferromagnetic materials with ferroelectric functional oxides, we can use the electric field generated piezoelectric string to control the magnetization of the ferromagnetic materials. In this way, we could generate a new approach to writing the information. The best heterostructure we like to have is epitaxial heterostructures. For example, if we can epitaxially roll single crystalline ferromagnetic metals onto ferroelectric oxides, that would be cool. Because in this condition, when you apply an electric field, the compressive string or tensile string will be exerted along certain crystallographic directions, and then you would have the largest modulation. But the growth of metal on oxides could be really challenging. For example, you first need a high temperature to have enough thermal energy to let the atoms of metals to go to their equilibrium size. But when you try to do deposition at high temperatures, the chemical reaction between oxides and the chemically reactive metals would be significant. And then you would have interfacial oxidation layer or the secondary alloying layer that will easily destroy the epitaxy. And the other important issue is the weighting issue, because the surface energies of the metals and the oxides are naturally different. It's like when you make a droplet of water on top of a piece of glass, there will be a weighting angle. So the metal films, especially at high temperatures, could not flat lay on the surface of oxides. That's also a big problem. The other thing is the lattice mismatch. Most of metals have a lattice constant around 3 angstrom, but for our oxides, especially for our perovskite single crystal substrates, they have lattice constants around 4 angstroms. So all these factors could lead to the unsuccessful epitaxy of metals or oxides. But we can always try to find a suitable substrate for a certain magnetic metal. For example, for this magnesium platinum, its lattice constant is 2.8 angstrom. It's a tetragonal structure. The in-plane lattice constant is 2.83 angstrom. And then we can choose this magnesium aluminum oxide. It has a spiral crystal structure. So after the in-plane rotation of 45 degrees, they can form epitaxy. And we can always try to optimize the growth conditions of the sputtery. For example, the argon pressure and the growth temperature and also the post-annealing temperature. You can try to make the growth slower and slower, try to simulate the growth conditions of the molecular beam epitaxy, and that makes the epitaxy easier. After the growth, by the sputtery, we can get the high quantity thin films of magnetic metals. Sorry, this magnesium, this MnPT is an antiferromagnetic metal. So with certain optimization and also with this sputtery, we can try to grow high quantity magnetic thin films, especially magnetic metals, onto oxide. And then we can try to testify our previous idea, whether we can try to use the piezoelectric strain to effectively control the magnetization of a ferromagnetic metal or an antiferromagnetic metal. This material is so-called iron rhodium. It's a metastable, it's a metamagnetic material. At low temperatures, it's antiferromagnetic. You can see from the left figure, the magnetization is negligible. This blue curve. But above 360K, it goes into a metamagnetic transition, and finally it becomes a ferromagnetic metal. So for this material, its lattice constant and its magnetization and also the resistivity are all strongly correlated. This phase transition, this metamagnetic transition, is a first order transition. When this transition occurs, the lattice constant has a sharp jump. And also because of the first order phase transition, it has a thermal hysteresis. When you try to warm up this material through the phase transition temperature and then cool down through the phase transition temperature, you got a hysteresis. So this would be an ideal material if you try to use the piezoelectric string to modulate its lattice, and then its magnetization, its resistivity will all be changed. And then we try to grow this metal on ferroelectric oxides. For example, here we use barium titanium oxide, BTO. It's a very typical ferroelectric oxide. Because of the relatively good lattice match, we can easily grow iron-rhodium, this metal, onto BTO. From this 360-degree fast scans, we can see this is an in-plane 45-degree rotation epitaxy. If we make the growth slower, we can get a relatively smooth surface. For example, the growth mode could be tuned into a quasi two-dimensional growth. And if we look at the transmission cross-section TM image, we can get relatively good interface and also the crystal niche of the ferromagnetic metals. Now, let's take a look at what happens if we apply an electric field or a piezoelectric string. And 100 Celsius degree, the iron-rhodium thin film is ferromagnetic at 0 electric field. It has lots of ferromagnetic domains. But when we apply an electric field, this electric field will generate a small piezoelectric string via the barium titanium oxide substrate. And this string will be transferred to the top iron-rhodium thin film. Accordingly, all the ferromagnetic domains disappear. This suggests that a small piezoelectric string could be very useful for tuning the magnetic phase of iron-rhodium, especially at around its phase transition temperatures. And if we look at the transport curves, the resistance as a function of temperature, which could easily give you the phase transition temperature, for example, this sharp drop, and also the two sharp drop in resistivities are corresponding to the metal magnetic transition temperatures. At a 0 electric field, the transition temperature is known, it's around 350 K. But when you apply an electric field that generates a tiny piezoelectric string, and then the phase transition temperature is tuned up to 370 K. So around the phase transition temperature, at a 0 electric field, previously it was already in the ferromagnetic phase. But when you apply an electric field or a piezoelectric string, this thin film is tuned into an antiferromagnetic phase. Therefore, the resistivity of this material is not varied. For example, it has a 21% resistance change at around 100 Celsius degree. So this is really a remarkable value for metal material, because metals exhibit a large number of free carriers. If you try to dope electrons or holes into these materials, you could hardly change its resistivity. But by virtue of this kind of metal magnetic transition, a small piezoelectric string can change the resistivity significantly. If we try to calculate the energy consumption for such a memory cell, we can get a value of around 10 to minus 17 joule per bit. It's like 5 orders of magnitude lower than the STT-RAM, MRAM, and 7 orders of magnitude lower than the MRAM. That's all because of the suppression of the Joule heating. We also try to compare the mechanism for different phase transitions between temperature-driven magnetic phase transition in iridium and also the isothermal piezoelectric strain-induced magnetic phase transition in iridium. We found for this piezoelectric strain-controlled one, electric field-controlled one, the dominant mechanism is the tetracality. That means the symmetry of the material. As we know in solid state physics, symmetry decides everything. For example, its electrical properties, magnetic properties, optical properties, and also some other even like thermal properties. So symmetry is everything for solid state physics or for condensed matter physics. So the piezoelectric strain control of magnetization is predominantly from the tetracality change. And now, based on this work, we try to start out our field, so-called the antiferromagnetic spintronics. If we compare our antiferromagnets with the well-known ferromagnets, they exhibit some obvious advantages. For example, they don't have remarkable stray fields. That means if you make the antiferromagnets as a key media for storing information, you can make the data bit quite close to each other. You can even make this so-called high pack density. You can get a high pack density. And because of the zero stray field, antiferromagnets are rather alert to external magnetic fields. So they are insensitive to external magnetic fields. This could be an advantage or a disadvantage. Depends. It depends whether you try to store the information or try to write the information. On the other hand, due to the canting of antiferromagnetic spins, it has a so-called antiferromagnetic exchange interaction. The intrinsic spin dynamics for antiferromagnets is very fast. It could be 3 orders of magnitude higher than that of ferromagnets. It can simply reach terahertz. If we look at this simple comparison mechanism between ferromagnets and antiferromagnets, for ferromagnets, the characteristic spin dynamics frequency, so-called the FMR frequency, ferromagnetic resonance frequency, is around gigahertz. It's like simply gamma. HE, gamma is the gyro magnetic ratio, and HE is the anisotropic field. But for antiferromagnets, because of the antiferromagnetic exchange energy, so its resonance frequency is like around terahertz. The pioneering for using antiferromagnets as key elements for spintronic devices came in 2006, that from Prof. McDonald's group at UT Austin. Actually, Prof. McDonald is a really very famous professor because he predicted the magic angles for twisted graphene, bilateral twisted graphene, and also other very important. He made lots of pioneering works for spintronics and also for the graphene field. At that time, Prof. McDonald called this field as antiferromagnetic metal spintronics because at that time, the study of antiferromagnetic insulators was very rare. But now the studies on metals and insulators with antiferromagnetic ordering quite often. So now we simply call this antiferromagnetic spintronics. In 2011, Prof. Yang was group at Keck, actually who was ever a postdoc of Prof. McDonald. So they reported a spin wave-like magnetic resistance of antiferromagnetic based tunnel junction. In this junction, they replace the positions of the ferromagnetic metal and the antiferromagnetic metal. They try to use an antiferromagnetic metal as a key element for a tunnel junction. What they did is they tried to use the exchange spring interaction between an antiferromagnet and a ferromagnet. Try to use the external magnetic field to rotate the spins of the ferromagnetic layer, this nickel iron. And then, because of the exchange spring, the antiferromagnetic spin axis in iridium manganese is also slightly changed. As a result, the tunneling resistance has a significant change at low temperatures. But unfortunately, these devices could not work at room temperature because of the very weak coupling of the exchange. In 2014, Ramesh's group at UC Berkeley reported a prototypical device that called room temperature antiferromagnetic memory. They still use iron rhodium as the key media. They use the metal magnetic transition of this material, and they apply a large cooling field, try to ping the antiferromagnetic spin axis through the phase transition. In this work, they clearly demonstrate when the current is perpendicular to the antiferromagnetic spin axis or is parallel to the antiferromagnetic spin axis, the resistance of the antiferromagnetic material is different. They have a so-called anisotropic magnetoresistance effect, which is quite similar to the AMR effect in ferromagnets. But somehow, this effect is very small. It's around only 0.1%. Anyway, it's a first-time demonstration of a room temperature AFM memory. This already is a big breakthrough. In 2016, Prof. Yang's group, again, they started to work on a new material so-called copper, manganese, and arsenide. They use electrical current to generate so-called NEO, spin orbital torque, use an electrical approach to controlling the antiferromagnetic spin axes. And finally, they can also get a room temperature memory by virtue of the AMR effect. If we now look at all these interesting materials, including antiferromagnets and some other ferromagnetic materials, we could find that there's a large breakthrough in antiferromagnets, so-called non-collinear spintronics. If you have non-collinear antiferromagnetic spin structure, like a triangle structure, you could have the Alomos-Hall effect, you could have the spin polarized current, even though they are still antiferromagnets. They exhibit tiny moments of magnetizations. Let me briefly introduce this part. So the mechanisms of the Alomos-Hall effect was really controversial. So since its discovery in 1881, but now people finally get some consensus that the most of contribution comes from the intrinsic deflection, so-called Berry curvature, and the other contributions are just quite minor. Following this understanding, Prof. McDonald's group, again, they predicted there's a large Berry curvature for non-collinear antiferromagnets. For example, manganese-3 iridium, manganese-3 platinum. They made this theoretical prediction in 2014, and quickly, only like less than 1 year after the theoretical prediction, Prof. Lakatsuji's group at Tokyo University experimentally observed the very large room temperature Alomos-Hall effect for this antiferromagnetic metal, magnesium tin. And this could be another important breakthrough for antiferromagnetic spintronics. If we now look at the Alomsky effect in non-ferromagnetic systems, we have non-collinear antiferromagnets, we have non-magnetic two-dimensional materials, we can also have non-magnetic two-dimensional electron gangs. Actually, magnesium 3 platinum is a very unique material. It's quite similar to iron-rhodium. Below 360K, it has a non-collinear triangular spin structure. It's also antiferromagnetic. But above that, it goes through a mid magnetic Nike, also a first order phase transition into a collinear antiferromagnetic phase. So following our experimental experience of iridium, we try to grow this material on ferroelectric oxides and try to use a piezoelectric string to control its different antiferromagnetic phases. For example, we again try to grow this magnesium platinum on barium titanium oxide. We get this quite nice epitaxial growth. And for the electric characterization, we found a significant, remarkable room temperature Alomsky effect for its non-collinear phase, but for its collinear high temperature phase, antiferromagnetic phase, there is no Alomsky effect. Similarly, we use an electric field to generate a piezoelectric string via the barium titanium oxide. The piezoelectric string can modulate the phase transition temperature. Around its phase transition temperature point, the two antiferromagnetic spin structures could be turned on and off by the piezoelectric string or electric field. In this way, we could turn on or turn off the Alomsky effect. Indeed, for this kind of metals, we have, because they are not strongly correlated materials, they are not like the oxides. So we could get very nice theoretical calculation. For example, Prof. McDonald's group did a calculation for us. They found that for the strained magnesium platinum films, the Alomsky conductivity is 81, and experimentally we obtained 74. So that actually was quite close. This work was published in Nature Electronics in 2018, and Prof. Christopher Söders made a brief news and reviews for this work. He said, because of the suppression of the current and the Joule heating, this could be very energy effective. And also this work was highlighted by electric physics, that now we can use an electric field to turn on and off the Alomsky effect for an antiferromagnet. Also, this work was highlighted by Science. The title was Manipulating an Antiferromagnet. It was emphasized that one can use an electric field instead of a magnetic field or electric currents to manipulate the spin structure of an antiferromagnet. After this work, let's think, because for antiferromagnetic materials, non-collinear spin structures are really rare. Most of antiferromagnets exhibit collinear, just a simple antiparallel spin structures. And we then think about how about the string effect, string modulation effect for collinear, for just Euro collinear antiferromagnets. And then we continue to fabricate, grow this, the collinear antiferromagnetic manganese platinum. This 50-50 phase is a collinear antiferromagnetic phase on 2p-MPT, which is also a ferroelectric oxide. We found the resistance of this antiferromagnetic film is quite robust over external magnetic fields. For example, if you apply a non-external magnetic field, you only got 0.01% magnetic resistance. It's very insensitive to external magnetic fields. But if you apply an electric field, you can get more than 2% resistance change. This is actually quite large compared with the magnetic field effect. It's 2 orders of magnitude higher. And then if we look at our resistance curve, it's quite similar to the strain curve in the ferroelectric oxide. That means this effect is purely from the strain. And if we look at, we continue to perform some like other experiments to study what happens when we apply an electric field to the piezoelectric PMPT. We grow a cobalt iron layer on top of the magnetic platinum layer. So it generates an exchange bias at the interface. We found for different resistance states, the exchange bias was reversibly modulated by the electric field or piezoelectric stream. However, the thin ferromagnetic layer of cobalt iron, which is only of 2.5 nanometer thick, is not sensitive to the strain at this range, at this strain range. So we conclude that the variation in the exchange bias is due to the modulation of the antiferromagnetic spins by piezoelectric stream. That's why we have this kind of cartoon image to show how the antiferromagnetic spins could be changed by the piezoelectric stream. We then tested the data writing process under strong magnetic fields because there's no any current in this kind of approach. We only use a voltage that's applied onto an insulated oxide. So we can easily write information under strong magnetic fields, for example, 14 Tesla. There's no problem. And we also tested the stability of this kind of strain-induced resistance state. The resistance state is quite robust. At room temperature, it's very stable. Like for a continuous reading of around 10 days, we will have more than like 10,000 points. The resistance state is very small. The resistance change is very small. The variation, the fluctuation is very small. And also, remarkably, this resistance is quite robust, even under a strong magnetic field of 60 Tesla. That means this kind of antiferromagnetic memory is robust over external strong magnetic fields up to, for example, 60 Tesla. If we think why this is so robust, we can look at their near temperature, which is a characteristic of how strong your antiferromagnetic coupling is. For magnesium-3 platinum, if you apply 60 Tesla magnetic field, the room temperature magnitude resistance could reach around 2%, but for magnesium platinum, its near temperature is much higher. It's around 500 K higher than that of magnesium-3 platinum. We have very flat magnitude resistance curve. That means the antiferromagnetic coupling is very important for the stability over strong magnetic fields. If we compare our electric field controlled antiferromagnetic memory device with so-called electrical current controlled one, because you have the Lorentz force under strong magnetic fields, the electrical current controlled one could not work under strong magnetic fields. For example, at 12 Tesla, the information writing is the writing is almost gone. So you don't have the very clear high and low resistance states. I think that's a big advantage for electric field controlled one. So this work was published in Nature Nano in 2019, and it was again highlighted by Science. And it was emphasized that now one can use strain to control antiferromagnetism. If we now look at after this work, after our experimental work, lots of theoretical work were performed. For example, this Prof. Roger Lake's group at UC Riverside, they calculate the strain dependence of the antiferromagnetic spins for lots of manganese-based metals. And if you look at even the previous studies, this kind of phenomenon was also proposed by some groups in China, for example, like this BFO, bismuth iron oxide. Upon some piezoelectric strain, they also propose their antiferromagnetic spin axes could be changed. Even like a little bit earlier, in 2016, Prof. Kamel's group at UCLA, they also proposed the AFM spins could be rotated by piezoelectric strain. At Tsinghua University, Prof. Lan Cewen and Lin Yuanhua's group, they also proposed that the spin axis of nickel oxide could be changed by piezoelectric strain, and also lots of other studies. Now, if you look at the principle for this kind of piezoelectric strain controlled memory antiferromagnetic spintronic devices, the key element is the magnetostriction energy. That needs a strain and also need a magnetostriction. We all think that the magnetostriction exists for ferromagnets, but indeed it also exists for antiferromagnets. It comes from long-range magnetic ordering as well as spin orbital coupling. So we can now say, although antiferromagnets cannot sense magnetic fields, they can feel strain as well as ferromagnets. We also proposed this idea, so-called antiferromagnetic piezo spintronics, try to use piezoelectric strain to control antiferromagnetic spins. The last point I want to bring to the audience is that an interesting comparison between two types of strain. One is epitaxial strain. For example, if we do epitaxial growth for oxides, we will have static and irreversible, that will quickly relax from the interfaces. But for the piezoelectric strain, that's also short range. It could only the electron thickness range is around 1 to 30 nanometers. But for piezoelectric strain, it's dynamic. You can try to trigger it by electric fields, and also it's reversible. You can use positive, negative electric fields. It's 100% in-plane strain mediation via interfaces. So if you have high quantity interfaces, you could reach 100% in-plane, that is a strain mediation. And also it could be really long range, up to micrometers. So except for this piezoelectric strain control device, we can also use some other electric field approaches. For example, the ionic liquid. You can try to modulate the Fermi level of ultra thin antiferromagnetic metal, and then try to switch on and off the enormous Hall conductivity. And also we try to summarize all the possible electrical field approaches for controlling the antiferromagnetic spins. For example, we have piezoelectric strain, as I emphasized in this talk, and we can also have ionic liquid modulation. We can have also kind of electrochemical control, which I did not mention in this talk, but it could be really obvious. For example, if you have cobalt, ultra cobalt layer, you try to make a dielectric layer like aluminum oxide on top of it. If you apply an electric field, you can drive the migration of oxygen ions that can oxidize or deoxidize cobalt. You get cobalt, either cobalt or cobalt oxide. So you will have a ferromagnetic metal or an antiferromagnetic insulator. And the last one is electrostatic carrier modulation by dielectric materials, for example, strontium titanium oxide. And this summarization was published in Advanced Materials I think 2 years ago. So if any of you is interested, you could take a look later. And I think I will close my talk, and thank you for all your attention. Thank you.
Great, thank you very much. I think the presentation pace is excellent, especially for both the beginners and well-known the researcher, the experts in the field. This presentation is super clear. So I think now the session is open for quick Q&As. Probably I can ask one question first, and then let the audience prepare their questions. Now, if you have, for the audience, if you have questions, you can either type in the chat window, or you can directly turn on your mic and ask questions. So maybe I can ask a first question. Hi, Zhiqi. So recently we had also looked at PMMPT substrate. So we thought probably we can also do some strain effects. But when we got the PMMPT and we did AFM, we realized that PMMPT surface is a bit rough. So then, for example, if we want to grow ultra thin films, we haven't done it, but we felt it's maybe a problem because there could be a leakage or could be discontinuity or cracks. So did you encounter a similar problem, or did you polish the PMMPT and make it very flat? So how did you solve the problem? And also, I think in the field, they also can grow 5 nanometer, 2.5 nanometers. How did they solve the problem?
So actually, we had similar issues. For ferroelectric oxide substrates, their surfaces are not perfect because of the ferroelectric domains. But we didn't have too much difficulty for growing metals, because the growth mode of metals onto oxides is simply island growth. You would not expect layer by layer growth like the architectural growth of oxide on oxides. So the key for getting relatively smooth surfaces of thin films is try to make the growth slow. And for example, for your sputtery, if you have a sputtery, you try to make the substrate target distance larger, or try to use a smaller sputtery power. But for the pulsed laser deposition, from as well as I know, I think you can also try to use the PLD to grow metals onto oxides. For example, you could get very perfect platinum on oxides. That's very easy. But like for some intermetallic metals like manganese platinum, manganese 3 platinum, the growth of these materials by PLD could be tricky because of the nanoparticles.
I see.
So the surface indeed is not really a big problem for us. So I don't think you could really avoid this kind of surface roughness because they are ferroelectrics. They have different ferroelectric domains. The roughness is, you see via the atomic force microscope could be intrinsically due to the domain boundaries of ferroelectric domains. Okay.
Okay, great. Thank you very much. So basically, your material is perfect for PMMPT. You don't have this problem, and the POD could be difficult.
I also remember, probably Novak has ever tried to realize layer by layer growth of oxide.
I see. Right? I see.
Probably if they, of course, I think you still have a chance to try to overcome this difficulty. One way could be you can grow a thin buffer layer of oxide.
Okay.
Yeah, that would be nice. You can try to grow some maybe ultra thin, for example, 5 nanometer strontium titanium oxide, or a very thin magnesium oxide MgU layer on top of
I see.
PMPT. That could make the surface smoother.
I see. Okay. So any other questions from the audience?
Hello?
Yeah.
I have a question. For the piezoelectric oxide, how much strain can they apply? Because the film is on top of the piezoelectric oxide, is it the same strain that the film feels? Is it the same for the strain for the film feels as the piezoelectric oxide applies?
Okay. So the first question is how much the piezoelectric strain is. So this is it's around 0.1%. It's very small. It's only 0.1% in plane biaxial. It's a biaxial compressive strain mostly. Of course, for some materials you could get tensile strain, but mostly we utilize compressive strain in plane biaxial. It's very small, only 0.1%. This tiny strain could hardly be simulated by theoretical calculations. We ever had difficulties for theoretical understanding of the piezo strain effect, but although this effect is quite remarkable or significant for lots of electrical and magnetic modulations, but it's very difficult to be simulated by theoretical analysis because this strain is so small that you would not build cells. You have to build a huge cell to reflect such a small strain. But that's it's very difficult. And the second question is whether this strain can be mediated or can be transferred to the top film. Am I right?
Yes. Is it the same for the film that feels the same strain?
Yes. So that's actually the last page this page I emphasized. Of course, the strain transformation for macroscopic material for non-nanometer film materials depends on the mechanical properties of the materials. For example, Young modulus and other parameters. But for nanoscale materials, the detailed studies, especially the references I listed here, these three differences, especially the below two references, they found the in-plane compressive strain could be uniformly transferred to the top film, including oxide thin films and also metals. This kind of transfer mediation could reach 1 micrometer thick. So we can say for this micro nanoscale thin film heterostructures, we could have perfect 100% in-plane strain mediation.
Okay. Thank you very much. So it is the same for the film it's the same for the film and the piezoelectric oxide.
That's right.
Okay. Thank you very much.
Okay. And even like for this APR work and the PRB work, their study was based on the I think some like lanthanum nickel oxide superlattices, lanthanum nickel oxide, strontium titanium oxide, bismuth iron oxide. The authors grew this kind of oxide thin films on top of PMPT, and they also I think they performed the depth resolved XRD analysis. They found that the in-plane deformation of the top thin films is quite consistent with the substrate. Yeah.
Okay. Great. We have a question from the chat window from Tianli. She said it was a wonderful talk. So can you please comment on linear antiferromagnetism or non-linear antiferromagnet? Which kind of antiferromagnet can give higher SOT efficiency? Which kind of antiferromagnet is more promising for memory application?
Okay, these are actually 2 or 3 questions. Okay. So these are very interesting questions. They really come into the key areas of so-called antiferromagnetic spintronics. For collinear, so first I think I would like to ask this question from many different aspects. First, if you look at the magnetic database, collinear antiferromagnets are the most. Their number is the most. So we have most of the magnetic materials are collinear antiferromagnets. This is the first point. Non-collinear antiferromagnets, they are rare, but they could have very large so-called magnetoelectronic effect. For example, the Elomsford effect. If you have the Elomsford effect, you could use the Elomsford resistance to do encoding, to do memory devices. And for the SOT efficiency, that depends on the spin-Hall effect. The spin-Hall effect has, in my mind, it has like several different origins. For example, the first is the spin-optical interaction, SOC, spin-optical coupling. If your material has very heavy elements, the intrinsic SOC could generate high SOT efficiency. This is one point. Besides, the Berry curvature could be also an interesting origin for the SOT. For example, in the non-collinear antiferromagnets, except for the heavy elements that generates the intrinsic SOC and the SHE spin-Hall effect, you could have the Berry curvature originating from the non-collinear spin structure. This Berry curvature could increase or enhance your SOT efficiency. So it's very difficult to really compare which kind of antiferromagnet would have stronger SOT efficiency. That really depends. But the general principle is whether you have strong spin-Hall effect is due to the the heavy elements, or due to this symmetry breaking like Rashba or Dresselhaus spin-optical coupling, or you could have the Berry curvature from non-collinear spin structure to increase or enhance the SOT efficiency. This is the first question. And the second one is like a 3 question or 2 questions.
Which kind of antiferromagnet is more promising for memory application?
Okay, so actually both materials could have advantages and also could have disadvantages. For non-collinear antiferromagnets, because they have very strong magnetoelectronic effect, that means they could be turned on and turned off by external magnetic fields because of very small, tiny canted magnetic moments. It's around like a micro, not micro, it's around milli μb per atom. It's like 3 orders of magnitude smaller than the ferromagnetic moment. For example, for iron, we have 2.2 μb per iron. For non-collinear antiferromagnets, you can control their spin structure by external magnetic fields. And then you can also use their Elomsford resistance to realize memory devices. But this kind of memory storage could be easily destroyed by external magnetic field. Therefore, non-collinear antiferromagnets is kind of similar to the ferromagnets, but they have very small or very tiny stray fields. The advantage of this material is you could make these bits, either these data bits, closer to each other. You can make and also the spin dynamics is very fast, so you can try to picosecond to write the information, the electrical pulse. But for the collinear one, they also have disadvantage and advantages. For example, their disadvantage is it's very difficult to control, to manipulate the spins of collinear antiferromagnets. I think the piezoelectric string is an effective one, but you can also use external magnetic field. But once you can realize a memory device based on the collinear antiferromagnet, then the information is very safe. I mean, in terms of the stability over external magnetic fields. So Actually, the stray fields, the zero stray fields, is the advantage for collinear antiferromagnets, and also it's the disadvantage for storing information. So how you can really easily control the spins in collinear one. So I don't think, so I think both materials could be very interesting from fundamental studies, but like for real applications, they also have disadvantage and advantage. So that's my answer. Thank you.
Okay, great. I think it's already 2. Yes. Yeah, okay. Tianli, you said thank you. So I think it's already 2 minutes past 11. We already we're already 2 minutes over schedule. So we probably have to close the Q&A session. And thank you very much for attending the seminar. And also we thank our speaker. Thank you very much. Thank you. So here is the end of the seminar. Thanks. Thank you.